Let's continue our look at entropy by looking at a special situation when we have phase changes. We can actually numerically calculate the entropy for a phase change of solid to liquid or liquid to gas or gas to liquid or vice versa. These special phase changes have names. Solid to liquid or liquid to solid is called the fusion change, and liquid to gas or gas to liquid is called the vaporization change. And when we looked at enthalpy, we had an enthalpy of fusion and an enthalpy of vaporization. With entropy, the amount of microstates of a system, we use these enthalpies to calculate the entropy of fusion and the entropy of vaporization by taking the enthalpy and dividing it by the absolute temperature. Entropy and the enthalpy and dividing it by the absolute temperature. This has to be a Kelvin temperature. This has to be a Kelvin temperature right here. And these enthalpies of fusion and vaporization are quite well known depending on what the substance is. Remember, this is a special situation only for phase changes. Also, another way we can calculate entropy is for particular reactions. And one of the main ways we can calculate the entropy for a chemical reaction is by determining the change in entropy of the summation of what's called the entropy of absolute entropies of the products minus the summation of the absolute entropies of the reactants. These little circles right here mean that we're at standard conditions, which means we're at 1 mole of substance, 25 degrees Celsius, and 1 atmosphere. And in your appendix of your textbook, there's a huge long list of the absolute entropies for many substances. Here's what Appendix C looks like. And if you look really close at the top, you can notice that there's a list of the enthalpies in kilojoules per mole. And then here are the entropies in joules per mole Kelvin. And you'll notice this column right here gives you entropies for many different substances. When you slide over, you can get more of them right here. And notice the units. This is in joules per mole, and the enthalpy is in kilojoules per mole. This will come back to haunt us in a little while. There's several more pages of these and these entropies in your Appendix C of your textbook. We're going to do one example problem like this from page 829 in the 13th edition. Sample exercise 19.5. And in this particular problem, they ask us to calculate the delta S from tabulated entropies. You can see the entropy equation right up here. And they give us a number of absolute entropies right over here, standard selected molar entropies. But here's the problem we're going to work. It says calculate the entropy change in the standard entropy system, the change in standard entropy of the system, delta S, for the synthesis of ammonia from N2 and H2 at 298. So for this particular problem then, we would want to do the delta S of the reaction at standard conditions is equal to the summation of the entropies of the products multiplied by its coefficient minus the summation of the entropies of the reactants multiplied by its coefficient. And just looking up these numbers in Appendix C, you can take a moment and look them up if you'd like to, but I'm just going to give them to you if you would like them as well. The entropy for NH3, which is the product right here, don't forget we have to multiply it by 2. The entropy for NH3, I'm going to put them on this piece of paper right here, 2 times NH3 is 192.5 joules per mole Kelvin. And then we'll find and subtract that, or find the difference between that and the reactants. And we have 2 reactants, nitrogen and hydrogen here. And for nitrogen, we'll multiply it by 1. It is 191.5, also joules per mole times Kelvin. And add that, because that's what this little symbol right here means, is add them together, times 3 of 130.6 joules per mole times Kelvin. Add those together, subtract it from this, and we should end up with negative 198.3 joules per Kelvin. Now, does this go with our prediction of a reaction like this? We go from 4 moles of gas to 2 moles of gas. Would we expect the entropy to become more arranged or more ordered? Yes, it is a negative entropy right here once we do calculate it from the Appendix C values. Well, now we're set to be able to put together H and S. Put together H and S to answer the question more and predict whether a reaction or a system or a process will be spontaneous or not, whether something will happen without outside intervention or not. This is put together into an equation called the Gibbs equation, or the Gibbs free energy equation. The Gibbs free energy equation is symbolized by the letter G, and it equals enthalpy minus absolute temperature in Kelvin times the entropy. This is called the Gibbs free energy, and the Gibbs free energy is measured in kilojoules. It's an amount of energy. H stands for enthalpy, and it's amount of heat energy at constant pressure, measured in kilojoules. T, once again, is the absolute temperature in Kelvin. And then S, of course, is entropy, which is measured in joules most of the time. And so watch out, because these units have to be converted to kilojoules almost all the time. So this is one way to calculate whether something is spontaneous or not, and G gives us a clue as to whether something's spontaneous or not. And it actually just gives us a numerical value that's positive, negative, or 0, and tells us where we're at. One other way to calculate this Gibbs free energy to answer that question is to do the same type of thing that we did with delta H and delta S. There on your thermodynamic quantities table in Appendix C are also Gibbs free energies for many different substances. Molar free energies or Gibbs free energies are listed right down the middle here and also down the middle here. And to find the Gibbs free energy at standard conditions, that's what the little circle means, is standard conditions, we would do the summation of the Gibbs free energy of products minus the Gibbs free energy of reactants. So what does this actually mean if we calculate G? Well, G helps answer the question, spontaneous or not. If G is negative, it means it's spontaneous in the forward direction. If G is 0, it means we're at equilibrium. If G is positive, that means we're non-spontaneous. That means we're actually spontaneous in that reverse direction. We'll pick up with some example problems of these Gibbs free energies and answering the question, spontaneous or not, in the next video cast.